So in this lecture, we'll continue talking about concentration inequalities, but we're going to focus on a different setup. We're going to talk about concentration of martingales. So we talked about concentration for sums of IID random variables. We also gave an example of concentration for sum of random variables which are not IID. They are independent but not identically distributed. But this is really a different setup. So when you're talking about martingales, martingales are not sums of random variables. They could be sums of IID random variables. These are martingales, but they are much more general. But before we dig into the setup and what type of concentration inequalities we're going to talk about, we need some preliminary results. So mainly we're going to need a lemma that talks about it's a bound on exponential moments of bounded random variables. So suppose that we have some random variable x, and suppose that you have two constants a and b, and that x is always almost surely bounded by a and b. So x is here in between, and the expectation of x given some sigma algebra f prime is 0. Then we can bound the exponential moment. So we know that the exponential moment of x is finite because x is bounded, right? But we have a very explicit bound on this exponential moment, and it's given by e to the 1/8 h squared b minus a squared. So this is a very explicit bound, and this lemma, you can think of it as a very technical. Oh, sorry, I forgot something here. This is true, but we have something more. We have also that the conditional expectation is bounded. So this is a technical lemma. We are going to use it in the middle of the next proof of the main result of this lecture. But it's better to get rid of the technicality soon, prove this lemma. But in essence, what you can think of it is just that it's a more explicit bound on this exponential moment that you know is finite. So what's the proof? So we know that x has finite exponential moments, so this is definitely finite. We want to use that x is centered. So instead of just trying to bound this directly, we are going to first relate this to some linear function, because linear functions behave very well with the expectation. So we can use the fact that this expectation is 0. So what do I mean by this? So we know that for every little x, the exponential of hx is a convex function. So we can bound it by theta e to the hb plus 1 minus theta e to the ha. Remember that x is somewhere between a and b. So we can choose any value for theta, and we're gonna write a very explicit value here that gives us the exact combination between a and b that gives me x. So if we want to use this inequality, we have to put theta such that theta is the right convex combination that gives x as a combination of a and b. And what's this? It's x minus a over b minus a, and b minus x over b minus a. Let's see why this is true. So if we sum this and this, we get x will cancel, and we get b minus a over b minus a. So indeed, this can be written as such, because the sum is 1. Also, if you look at this value here, so this is multiplying so this is this distance here normalized by b minus a, and this is this distance here normalized by b minus a. So these are the two combinations that give x indeed. Now this is just applying convexity, and what's the advantage of this is that if we take now the conditional expectation on both sides, and now big X instead of little x, then the expectation of x is 0. So we're gonna get, I'm gonna invert this, I'm gonna put the first term here. And the second term here. You see that we have that the terms of x have disappeared because the conditional expectation of big X is 0. So we have already exploited the linearity of conditional expectations. So now you see that this thing here is something that we can write just as P. Sorry, I'm gonna write this thing here as P, and this I'm gonna write as 1 minus P. So remember that A is negative, right? So A is smaller than 0. So minus A over B minus A is still a positive number. So that's why we are calling this P. And this is 1 minus P. And we're gonna define as well Y. This is just a change of variables. Is B minus A times H. So with these two changes of variables, we can write the above as 1 minus P e to the minus P y plus P e to the e to the 1 minus P y. So let's double check this. So this is clearly 1 minus P. Exactly, this is P. They sum up to 1, right? And this in the numerator is A. Sorry. Yeah, this is HA. So it's the first term here. HA is minus B. Sorry, let's double check this. So here we have Py. P times Y is minus A over B minus A times B minus A times H. So correct. Here we have minus A H. So here we have a minus sign, so it's AH. So this is correct. And on the other side, they have 1 minus P y, and instead of only the minus A surviving, we have the B surviving, so it's going to give us HB. So this is correct. And we can rewrite this again as e to the minus Py. So we're putting e to the minus Py outside. And then we have 1, this 1 here, minus P, this p, and plus p e to the y. Sorry. Yeah, this py goes outside. There is a y left, so that's correct. And if we call f, if we define f of, say, z to be minus py, this term here, plus the logarithm of what's here, 1 minus p plus p e to the x, e to the z. Here is also z. Then we can rewrite this as simply e to the f of y. So it's just a convenient way to take this and write as an exponential, because in the end, what we want is just an exponential. So we don't want this exponential times a polynomial. So we write f as such, and we can write everything as an exponential. But now we have this weird function here, and we have to understand how this function behaves. And this is going to be very similar to what we did in the last class, where we were studying the sum of variables between 0 and 1 that were not identically distributed. We have something and we want to find an upper bound for it. So first we take the value of the function at 0. This is going to have a 0 here, and this e to the 0 is going to give 1. P minus p is 0. Log of 1 is 0, so this is 0. Then you take the derivative as a function of z, and this is going to give us minus p from here, plus we have the same denominator here, 1 minus p plus p e to the z, and in the numerator we have the derivative of this with respect to z, which is p to the z. If we evaluate this at 0, we get minus p, and in the denominator you have 1, in the numerator you have p. So it's minus p plus p, which is 0 again. So I have a function that is 0 and the derivative is 0 at 0. Now I'm not gonna do the whole computation. This is just a boring computation in the end. But we can take the second derivative of f, and the second derivative of f is just p 1 minus p e to the minus z over p plus 1 minus p e to the minus z squared. So it's a ugly formula. But this is smaller or equal than 1/4. You can check this, because you can use the fact that the arithmetic mean is always a bound for the geometric mean. So this is similar to what we did previously, bounding the tail of the composition of f. We know that f is above a certain parabola because of the Taylor's formula with an intermediary value theta. So in the end we conclude that f of z is always smaller or equal than 1/4 times 1/2 times z squared. So it's z squared over 8. So in the end, that's what we obtained. So here, the conditional expectation is bounded by e to the f. Sorry, here is a minus that I forgot. So the conditional expectation of e to the hx is bounded by e to the minus 1 we wrote f, we had f of y here. So this is e to the minus, so this is smaller or equal than e to the minus y squared over 8. So we have to recall what y is. Y was b minus a over b minus a times h. So this is e to the minus h squared over 2 times b minus a squared, as we as we wanted. So this is the proof of this technical lemma. The proof is again just use the convexity. Now there is this trick of using the conditional expectation to remove the terms in x, and now it's just a bound of real analysis. It's a bit of a boring one. We have to take two derivatives, but this is just the proof. Now what we're going to do with this is prove a very nice result about concentration of martingales, which is due to Azuma and Hoeffding. So suppose that we have a martingale xn, and when we say that something is a martingale, we always mean with respect to some filtration f. And let's also suppose that the increments of x, of the martingale, denoted by yn, so this is xn minus xn minus 1. So this was for n larger or equal to 0. This is for n larger or equal to 1. So this is the increment of our martingale. And we assume that the increment is always between some ak and some bk. Right? So we know that the expectation of y is 0 because the expectation of a martingale never changes. So this is why this is connected to, you can see already some inspiration from the last lemma appearing here. And we fix some, we want to bound in the end the probability that our martingale has deviated from its expectation. So we know that the expectation is 0, so this is just the deviation. So we know that this is bounded by e to, so it's an exponential decay, 2t squared over the sum over k from 0 to n of bk minus ak squared. So up to now, it's not very clear how to apply this inequality, if this inequality is good at all. But we can already observe a few things. So this is an exponential decay on t squared. So it sounds a bit strange to have a t squared here. Let's take a look at what happens if you use this theorem for a martingale given by a sum of IID random variables. So for example, if psi i's are IID, psi is distributed as delta of minus 1 plus delta of 1 over 2. This is a standard thing we do. Then xn being the sum of psi i's, we could try to use the above. This is going to be a martingale whose increments are bounded between minus 1 and 1. We could obtain something. What do we obtain? The probability that xn minus x0 is 0, so is bigger or equal to t. And what we are going to choose for t here is some epsilon n, because we know that this should deviate of order epsilon n. This is going to be bounded by exponential of minus 2. So t is epsilon n, so we have here epsilon squared n squared over, so this is 2 again. This is 1 minus 1, so this 2 square gives us 4. And we have n times this, so it's 4 times n, which is exponential of minus epsilon squared, the n cancels, over 2. So you see that it's very similar bound to what we already have proved for sums of Bernoulli random variables. So this is a nice result even in the case where we know much more about these random variables. It's an exponential decay. In typical situations where this is of order n, this is going to be n squared, and there will be an n here as well. So in typical situations, we get the usual exponential decay that we have. But now we are going to prove the theorem. And after we prove the theorem in the next class, we're going to give some applications that are really going to show how different this is from the typical IID case, how more powerful this theorem is. So for the proof, we're going to start with the usual suspect. So we have a probability that we want to estimate here. Oh, by the way, t should be positive. So we know that t is positive. We can multiply both sides by h and exponentiate. So here we get this small or equal. So actually, let's go slowly. This is equal to the probability that e to the h xn minus x0 is bigger or equal than e to the ht, which by Markov's inequality is bounded by the expectation of e to the h xn minus x0 times e to the minus ht. So we already have an exponential decay here. Good. Now we have to bound this expectation by something that is also, it's going to be exponential. It's most likely going to be something that grows exponentially, but hopefully this will go to zero fast enough to compensate. And we still live with an exponential decay. Now, we can already see that here we have something similar to the sum of IID random variables, because we can always break this into a telescopic sum. And this is going to be the sum for k from 1 to n of yn. Right? Yn are exactly the increments of x. So this, we did nothing, but it looks more like the sum of IID random variables we had before. If you remember, okay, exponential of sums are just products of exponentials. So this we can do as well here. But the problem is that we cannot take the product outside. This is not a set of IID random variables anymore. This is the whole point of Azuma inequalities, to break with the IID assumption we had before. But anyway, we want to bound this. So let's call this I. And let's start bounding this without, of course, using the independence, because it's not true. So we have this exponential of a sum. So I k here. And the first thing we do is to take the conditional expectation with respect to fn minus 1. So we can always do this. Okay. Now, of all of these terms, they always break into product, but several of them are going to be measurable with respect to fn, because this is just yk is xk minus xk minus 1, and both are measurable with respect to fk. So we can remove several of these terms outside of the first conditional expectation. So we're going to have e to the h sum up to n minus 1. Sorry, k equals 1 up to n minus 1 of yk. And we still have here the conditional expectation of e to the h yn given fn minus 1. So let us, now it's really like we had in the previous lemma. Let's go back to the previous lemma. We had a random variable. In our case, underneath it's going to be y. The conditional expectation of y, we have to check that it's 0. Then we can bound the conditional expectation of the exponential by something. So let's go down and see if we have everything we want. So this is going to be our random variable. What's the conditional expectation of y given fn minus 1? Sorry, yn. This is going to be xn given fn minus 1 plus, sorry, minus the expectation of xn minus 1, but xn minus 1 is measurable. But this, by Martingale property, is exactly 0. So we have the good hypothesis we need. We also know that y is between an and bn. This is a hypothesis of the current theorem, that yn is between an and bn. So we can use the previous lemma to bound this by a number. So this number goes outside. That number was exponential of minus h squared over 8 bn minus an squared. And now we have the expectation of e to the h sum of yn, of yk, sorry. And we can use induction because we just removed one term here, and we can use induction in all the terms to get in the end the exponential of minus h squared over 8. This is the common term, and then you get a sum, okay, from 1 to n of bk minus ak squared. So we had in the end we obtained the bound on this exponential moment in terms of something that's sorry, what did I do? No, I completely I put a minus that doesn't exist in the lemma. So this is a plus. So we finally obtained the bound on this, which is too bad it's exponentially growing, but we hope that it's gonna be smaller than this. So in the end, the probability that xn minus x0 is larger than t is bounded by exponential. Here you have h squared over 8 sum but we also have minus ht from the denominator term here. So now we just have to choose h, and the choice of h is the one that minimizes this. In the end, we just choose h to be t over 4 the sum of bk minus ak squared. So this is our choice of h. So here when we take h squared, so this is just a choice. H squared is going to have a t squared here, right? It's going to have a 16 in the denominator times 8. We have this in the numerator and twice in the denominator. So in the denominator, we still have a sum like this. And now on the other side, we have, again, t squared, because there's one t for h and another t here. In the denominator, we have just a 4. And this sum, which is not squared anymore. So let's copy this to the next page. So you can see that this term and this term, they are just a constant apart. So in the end, it's 1 over 2 to the what? 3 plus 4 minus 1 over 2 to the 2. So this is minus 2 to the what? 2 to the... It's not as simple, right? Whatever. We get... Let's complete here. We have 2 to the 5. I think this is wrong. Somewhere I may have made the mistake. So it's 2 to the 5 minus 1 over 2 to the 7. This looks strange. So there's something wrong here. One over 8. Oh, I see what I mean. The mistake I made. The 1/4 here, it's not 1/4, it's 4, right? Yeah, I think it's a 4 in the numerator. That's why it was wrong. So here, I think it should be a 4. Then we have a 16 here and a 4 here. Yeah, correct. Sorry for that. So this will give us 2. And here we have a 4. So in the end, we forget all these crazy things in the denominator. Here we have a 2. Here we have a 4. And in the end, we get the result. So essentially get this is equal to e to the minus t squared minus 2t squared over the sum. So let's look at the result we wanted, and this is exactly what we have. So this finished the proof of Azuma-Hoeffding's inequality. I hope I convinced you that it's not similar to what we have proved before, in the sense that it's not dealing with IID random variables anymore. It's just a martingale. In the proof is exactly mirrored in the other proofs. We're gonna take an exponential Markov inequality, but when we take such an exponential inequality, we have to calculate exponential moments. We cannot break it into the sum anymore, but we can take these smart conditional expectations that have essentially the same effect. And in the end, we get the bound we want. What I have not convinced you perhaps is that this is more useful than the IID case because, you just saw martingales. So maybe the example of martingales you have in mind is this, which is just a sum of IID. So in the next class, I'm going to give other examples that apply Azuma's Hoeffding's inequality into other contexts, and you're going to hopefully see that it's way more powerful than what we have seen so far. So see you.